Thank you very much. I would like to thank SAGES for the opportunity to present the work we've been doing at University College. And the timer is on.
You can go and start.
I've got no conflicts of interest to disclose. We're going to discuss the problem of standardization of perfusion-guided fluorescence, fluorescence-guided perfusion assessment in colorectal surgery, address the methodology that we developed to answer this question, and finally conclude with some planned work. So we know that perfusion assessment with ICG has been used in colorectal anastomosis. This led to an adjustment of the transaction point between 3.9 to 19% of cases, and this has been associated with the reduced leak with an odds ratio between 0.2 and 0.4. There has been consistent benefit in the available studies. However, we still don't have randomized data, and this is a significant limitation to the widespread use of the technique. One other problem with this technique has been the causal model for fluorescence angiography. What you see on the screen that goes through perfusion assessment, which leads to adjustment in the transaction point and lower leak rate, is, in our estimation, an incomplete causal model because it doesn't take into account surgeon variability. And we know that if we don't adjust for surgeon variability, we're going to have confounding in the results. And even the trials that, the INTACT trial, which is already ongoing, is biased by this, by not taking into account surgeon variability in the causal model. How do we want to adjust for surgeon variability? We're going to use computer vision. This is the subset of AI that automates tasks that the human visual system can do. This is done by gaining high-level understanding from digital images. You can see this small apple, which is magnified here. We can see the picture elements or pixels. Each pixel represents a specific set of numbers, which in this case is the XY coordinates and the color value in a specific color space, in this case RGB. This is what the computer uses as inputs in order to generate the prediction model. So we use the k-means clustering algorithm. This is an unsupervised method, which means that we don't use labeled data as inputs. This is applied in two steps. For segmentation, first we see background and foreground segmentation, which looks like this. So we can see on the top the image, the raw input data, and on the bottom the result of the background-foreground segmentation. And then we use, again, this same algorithm to subcluster the foreground into areas of different perfusion levels. We can see here, raw input, first step foreground, background segmentation, and then the clusters that define different perfusion areas. How does this look like? This is the output from this algorithm, which gives us an optimal transaction area. This is defined by the best compromise between distal perfusion on one hand and colonic lens on the other. So here is what we consider as the optimal transaction area as per this algorithm's output. Now this is what it looks like in sequence on the video. And here you can see another case where we have first foreground, background segmentation. You can see here the bloody swabs introduce an element of error, which I will address in the limitations. But again, you get an optimal transaction area here. How did we validate these results? So this image was presented, this and other images were presented to experienced surgeons, and they were given the choice of the optimal transaction area as per their experience by selecting one of these randomly ordered letters. We see that, again, as we hypothesized in the beginning, there is variability in surgeon choice, and we see that when we superimpose the results of our algorithm, we have a concordance in the area of 87% in this case and 100% in the other models. Now, some limitations need to be addressed. The fact that we were seeing linearly positioned colons led to those results that you saw. However, when the colon is not linear, as you can see here, the clusters that the algorithm identifies are abnormal, and this is an unacceptable result of the algorithm. So this is something that we need to work on. And also the fact that there's no context awareness. The fact that this is a swab and not colon needs to be taken into account, and the algorithm needs to recognize different textures and integrate that into the decision-making process. This is, again, something that we are currently working on. Now, we want to optimize the definition of the area of transaction. Right now, what you see are linear approximations, and we want to make this decision based on boundaries between clusters and not on a mathematical model. We also want more data, not only more cases, but most importantly, and this is, I think, one of the biggest benefits of being able to discuss this work in a larger audience, the fact that we are not standardizing data capture at the moment, and this presents a very important limitation to widespread development of these algorithms. The fact that every surgeon does what he or she wants or has become accustomed to is a limitation that we would like to address by discussing and achieving the optimal method to capture this data. And also, when we reach that point, we feel that we are in a position to start employing supervised methods. This is the outline of the retrospective data collection and analysis for the project GreenEye. We would love to have more collaborators from the audience. Feel free to use this email or get in touch with me after this session. Thank you very much for your time.